All amazing and very intriguing technologies. But I want to come back to this idea of empowerment and how the original classic ASP was really empowering for me, and how ASP.NET 1.0 and certainly 2.0 were equally, if not more so, empowering as well. And today I want to introduce you to what I consider kind of the third phase or the third instance of empowerment in my career, and that is with quite literally blinking LED lights. You may think I'm joking, and I am kind of, but really I think you'll see how this plays out today. But for the first time, I was able to write code that could interact with the physical world, right? So that is a long-winded intro to me and my talk. So quickly, who am I? I'm Rob Lauer. I'm Director of Developer Relations at Blues Wireless, which is a wireless IoT company. Previous to Blues, I spent quite a few years at Telerik and Progress. Some of you .NET developers may know us, I say us, who I was previously, for our web UI components and Kendo UI components for JavaScript developers as well. So I'm really here to talk about one of the many ways in which what we call web developers and embedded developers can really overlap going forward. So lines are really getting blurred as time goes on, as .NET and C# really can team up to provide a really positive way, I would say, in which I think software developers can move into the physical or move into the embedded space. And I'm not assuming any knowledge in this talk at all, right? Any prior knowledge about embedded development or the other Internet of Things or IoT. Therefore, I wanted to start with a really brief 101 level description of what embedded development even is. So embedded programming is this concept of writing code for incredibly small computers, aka microcontrollers. Those microcontrollers generally communicate with something like a component like a sensor. This one, for example, can measure temperature, humidity, and pressure. Maybe they power servo motors that in turn can control other machinery. So we're building these really small programs that run on highly constrained devices. And I say highly constrained in terms of like the processing power and the available memory and that kind of stuff. So these programs that we're writing are generally doing one or more of the following things. They're sensing something, they're measuring something, maybe they're tracking something or controlling something. So something physical, right? And in the embedded space, you'll hear this term firmware kind of bandied about. All you need to know about what firmware is, it's essentially like semi-permanent software loaded into non-volatile memory on a microcontroller, right? On a device. It's not software, it's not hardware, it's firmware. So my journey from the web to the IoT without C#, it involves some serious Toolbelt changes. And change can be scary, especially for me. So I go from writing C# and some JavaScript to writing Arduino, C, maybe Python. My IDE changed, obviously. I moved away from Visual Studio into Arduino IDE, or if I was lucky, maybe VS Code with some helpful extensions or two. And really fundamentally moving away from working with the browser, working with those really mature and engaging dev tools that have been, been fantastic over the last 10, 15 years or so. And moving into, monitoring output from a serial port and dealing with physical things like cheap sensors that break, wires that corrode, conflicts in some communication bus, or power issues. I mean, it's just crazy the expansion of how difficult things can get. And to provide an example of kind of what an early simple program might look like in Arduino, which is very similar to C. Here is what's called an Arduino sketch, which is just some firmware, for instance, that reads data from an accelerometer and then returns XYZ values to indicate motion or movement. Now, while I've been getting more and more comfortable over the years with Arduino and with Python, it still doesn't mean I'm super happy about it. And my boss, I think, is in this room, so he's gonna take that as a note. But I knew at the time there was just something I could do about that, and let's hold on to that as I change context for a moment. So embedded development is the idea of programming a tiny little microcontroller, right? How does that relate to the Internet of Things or the IoT? I can boil it down by saying these things we are building often need an internet connection, right? Maybe they're uploading data they're gathering or calculations they're making or machine learning inferences they've generated. Maybe they need to receive data to perform a function in some kind of remote control scenario. So it's really adding networking capabilities to the device. But it is such a weird name though, right? The Internet of Things. Like when the web took off, we didn't call it the Internet of Personal Computers. We didn't call the early phone age the Internet of Mobility. Likewise, why do we set up the Internet of Things for failure by calling it such a silly, vague name? So pardon me for a moment as I get on my soapbox for a little bit here, because I have some opinions, some strong opinions about the IoT. For instance, you do a Google image search for IoT and you get stuff like this. It's like these nebulous web-looking things, right? Which tells me that nobody really knows what the IoT means, or doesn't stand for any one thing. It tries to be so many things for so many different people. And like I introduced the talk with, the IoT has a major perception problem, right? It includes internet-connected flip-flops. It's a belt that has an internet connection to your mobile device. It's a series of devices that we've learned over the years have issues with losing connectivity. It's got firmware updates that disrupt our workflow. They happen in the middle of the day instead of at night. They end up adding friction to our lives instead of removing it. It's new privacy concerns. It's new security issues. It's this example of like a security device that can't tell a human face from a face printed on a t-shirt. So all of these make the IoT super easy to dismiss as a fad, which is a big problem. If you're familiar with Gartner's hype cycle, this is why they peg IoT down here in the trough of disillusionment. But I would say there is hope. The IoT in general is still very much in its early stages, and it's a very natural next step as we advance from mainframes to PCs to mobility and beyond. Like, devices are doing what? They're getting smaller, and there's a lot more of them. So as mobility is maturing, right, we're entering into this wearable AR, VR, metaverse stage, which definitely includes the IoT, right? And we're talking about an almost immeasurable number of devices coming up. 75 billion devices, $15 trillion, as the analysts like to say. And I have 3 nice examples of real-world problems that are being solved by the IoT today. These happen to be 3 companies that we work with. I'm just putting them here, not to tout us, but just to provide like real practical examples. So American Crane and Equipment, they're using the IoT and our products to remotely monitor and diagnose issues without technologists having to travel. Pretty obvious use case. Another one is with remote monitoring on a different scale. This has to do with greenhouses in Colombia, monitoring flowers. They're gathering way more data than they ever could have previously by using the IoT, and they're putting all this data into really friendly cloud dashboards, right, to really simplify that process for them. The third is within the healthcare industry, another possible game changer for the IoT industry. There's a small company we're working with in the Caribbean who is actually building these devices and enabling these underserved populations to take devices home and communicate over cellular where they have no broadband, they have no internet access at home. So there's this bi-directional healthcare possibilities with the IoT as well. So I showed you those 3 examples to kind of demonstrate that the IoT really will succeed when it solves real problems in the embedded space, right? These problems where connectivity is critical. I like to say that connectivity is the secret sauce here, and IoT solutions that really focus on solving these real problems with connectivity are the key to legitimizing the industry. And that is the end of my soapbox. So I've talked about embedded development and the IoT at a very, very high level. Most of you are keenly aware of the journey that .NET has been on over the last 10 plus years. Therefore, it's time to address this Venn diagram of where these two overlap. Now, this for me is when the lights shone down from heaven upon 2 of these relatively new-ish .NET frameworks that are optimized to run on highly constrained devices, that being the .NET nanoFramework and TinyCLR OS. As an aside, what I'm considering out of scope for this talk is .NET Core IoT. You probably know today that you can build and deploy a .NET Core app on Linux. That also applies to relatively constrained devices like the Raspberry Pi platform. So .NET Core IoT really introduces some libraries that you can use to interact with sensors, with I/O ports, and with physical hardware that are connected to the Pi and other similar single-board computers. So is it IoT? Absolutely, yes, it is. The differentiation here today is I'm talking about building tiny apps, like tiny apps that run on tiny little devices, not on what is, comparatively speaking, a massive Raspberry Pi. So let's talk more about the 2 of these more popular tiny .NET frameworks for embedded development, those again being the .NET nanoFramework and TinyCLR. What do they both offer? Well, they are both completely free frameworks for using .NET, of course, to build embedded apps. They both let you write C# code. They both support Visual Studio 2019 and 2022, the community editions as well. And of course, being part of Visual Studio, you get all the great features of Visual Studio, integrated debugging, the build deploy process, and all that kind of good stuff. Both of them have fairly extensive library and device driver support, and they're available on NuGet. And so far, I mean, I painted a really rosy picture here, right? All good things so far. The downside is that both of them offer only a small subset of the .NET-based class libraries. This should not be a huge surprise really to anybody, because you can't really imagine, downloading and installing the entire .NET framework on a device with maybe 1 or 2 megs of flash to spare. So drilling in a little bit more to the .NET nanoFramework. nanoFramework does provide fairly broad support for a variety of really popular microcontrollers. So this is a big bonus. It is fully open source. It's MIT licensed. It is supported by the .NET Foundation, which I know the optics of that can be good or bad depending on previous projects you've worked on that are supported by them. Most intriguing from my perspective is they are working to align the nanoFramework with the .NET Core IoT APIs. So these bindings that they call them can be like sensors, displays, other embedded components from the same family, for instance. Likewise, TinyCLR stands out in its own ways. What's interesting about them is they are more focused on tightly integrating with their own proprietary microcontrollers, and those are the SIT core-based MCUs. My personal experience with TinyCLR is that the debugging process, even though it's same thing within Visual Studio, is a little more straightforward than nanoFramework. I also found their getting started experience to be dead simple. You might think, looking at my previous slide, that nanoFramework is kind of a no-brainer to start with. I found that the real tight integration and the integration between the TinyCLR and the hardware made it a much more engaging experience, right? It just worked for me out of the box. So the rest of this talk does focus more on TinyCLR. I'll put that disclaimer out there. But virtually everything I cover applies to both frameworks. It might just be just small tweaks between the two. So I did want to talk briefly about some features of TinyCLR. Again, some or all of these exist in nanoFramework. First is multi-threading. This is not super common in the embedded space, but you can perform some basic multi-threading tasks. You can obtain type information at runtime, as TinyCLR supports reflection. Collections are supported as well, so those classes in system.array and system.collections are available for handling data, which is huge. And serialization, so this idea of converting the state of an object into something that can be persisted or transformed is available, as well as deserialization, of course. And again, since we're moving away from deploying to the web or the desktop or a mobile target, we have to deal a lot more with device drivers, with component drivers. TinyCLR, just like nanoFramework, they provide loads of drivers for some of the most commonly used components out there. Your mileage may vary depending on exactly which components, but a lot of them are out there and available on NuGet. Now recall I said that TinyCLR apps are bound to proprietary hardware. This is the line of microcontrollers and single board computers that they call them, offered by GHI Electronics. That's the company behind TinyCLR. You probably can't read it, and maybe you can. All of these are prepended with FEZ, F-E-Z. It stands for fast and easy, which was my experience, I will admit. Today, I'm going to show off this one. It's the FEZ Feather. It utilizes the Feather standard, the Adafruit Feather standard. It's a really nice option if you have a lot of peripherals that you're connecting to, because there's a lot of I/O options, a lot of pins to use. But really, for the demos I'm going to show today, this would absolutely work on any of these products, including, I love the little flea on the end there. It's very, very tiny. So what is it like to get started with TinyCLR OS? I was going to show you live, but it's actually super simple. I'm just going to go through it in a couple of slides here. There are no drivers to be installed. You kind of just plug it in and everything sort of just works. Obviously, your first step is to plug it in via a USB-C cable. First thing you have to do is you flash the TinyCLR OS to your hardware, and there is a TinyCLR config utility available for that, Windows only. Then in Visual Studio, you just have to install the TinyCLR OS project system extension. And when that is done, you create a new project of type TinyCLR application. Really, that is all there is to it. So that gives us a program shell that we can literally one click, hit the start button, build, deploy, debug on a connected device just using Visual Studio. So with that, let's do our first little demo here. I'm gonna do a little hello world and hope to God that Parallels doesn't screw up my HDMI connection here. And this is gonna work. So far, so good. Kind of. There we go. Okay, so this, and I tried to increase the font size. If anybody needs it larger, let me know. I'm gonna walk through some parts of this code. It's very, very simple. This is not earth-shattering in any way. The only thing that is amazing to me is that we're gonna build and deploy this on this little guy right here. And of course, the first thing everybody has to do when they get into the IoT is they need to flash an LED. Most, if not all, microcontrollers come with an onboard LED. It's very useful for stuff like this, when you want to just make sure you have a proper connection and you can build and deploy code that just works. So at the top here, I have some libraries that I'm importing, right? I need to access some GPIO, some pins on here. I need to use the system.threading for a sleep, for thread.sleep as well. The important thing you need to know here is that I have this main method. This is the method that gets executed as soon as I start this program. And I'm going to create a reference, as it says here, to the onboard LED via pin 11. How would you know it's pin 11? Every microcontroller comes with what they call a pinout diagram that'll tell you which pins correspond to what features. And so I know that the onboard LED is on pin 11. And then we get into this crazy thing called an infinite loop, which those of us in the web or desktop space generally don't deal with too often, or if we do, it's for a bad reason. In our case, it's a very good reason, because we want, when we power up this program, we want it to run forever, generally speaking. So what do we do? Well, we simply set we set our pin value, pin 11, to high, which means turn it on. And then we sleep for 100 milliseconds. Then we set it to low, which turns it back off, sleep for another 100 milliseconds. Again, this is not earth-shattering here, but it is kind of cool to be writing C# and dealing with microcontrollers. Let's see if this will break my... So, that's good. Yes. All right, so far so good. And all I'm gonna do, like nothing up my sleeves here, I'm just gonna hit the start button here. And 50% of the time, this works every time. I do occasionally run into these very vague errors, and I've learned that if I just do it twice, it works. And one thing that's very interesting to me is, yes, allow again. It takes a surprisingly long time to compile and deploy an app to a tiny device like this. Now, part of the reason too, I'm using Parallels on an M1 Mac, on Windows ARM, with Visual Studio that's not supported on ARM yet, connecting USB, it's all crazy and everything. Anyway, here we go. So I got my little Blinky LED, so it actually did work, which is awesome. Now, one thing I can show you really quickly is, let's just close that. Oops. Docu. And just briefly show off debugging. This is not going to be too astounding to anybody. I can just set a breakpoint and I can hit start again. And it should just do a quick rebuild and redeploy to the device. Sure. And I can go through, and as soon as it hits that breakpoint, I can perform some step into debugging like we've all been doing for years. Now this to me is really amazing, because now I'm actually debugging an app that's running on this separate device over here, which, I don't know, I think that's really cool. So now, let me see, you know what I'm gonna do? I'm gonna quit this. Whoops. I just don't really trust anything. And while that's running, I want to pivot into the eye of the IoT and talk more about like what the internet means, what the internet part of embedded development really means for us, and then get to our second demo. So this has more to do with what the company I work for, Blues Wireless. Blues was founded and led by Ray Ozzie, who is, if you know of him, he basically kicked off Azure at Microsoft. He was a big figure in Lotus Notes back in the day. Blues is really here, and the reason I'm here today more is to talk about the hardware and services that we build and provide to make wireless IoT easier for developers and more affordable for all. And if that is our core mission, how do we go about accomplishing that? I think just as developers, you will appreciate some of these. We are all about securing data from the device all the way through to the cloud, building zero config, low power hardware. So low power hardware, low power defaults in the firmware as well. And then really providing an unmatched developer experience. So we're very, very, very focused on the developer and that developer experience. Zooming in on our hardware super quickly, the note card is the core of what we provide. It is a low power system on module. It measures a tiny 30 by 35 millimeters. I've got one up here that I'll show you in a second. There are both cellular and Wi-Fi versions of it. The cellular comes with GPS as well. The cellular version comes prepaid, 500 megabytes of data, 10 years of global service. The API, the way you interact with the note card, is all JSON based. This allows us to build SDKs for Python, Go, Arduino, C, C++. We have a community supported integration that I'm going to show you today that works with nanoFramework and TinyCLR. So again, everything with the note card is JSON in and JSON out. As an example, if you wanted to get your card's location, your note card's location, you simply call this card.location request in JSON format. And that's going to return a response with the latitude, longitude, some other metadata. The rest of the API is set up very similar to this. The other part of the equation is NodeHub. NodeHub is the Blues Wireless cloud service that receives data as a proxy from the note card. This is because the note card does not live on the public internet. It is a very secure device. It does not have a public IP address. So it needs a proxy in the cloud to receive data. However, NodeHub will transparently route your data to whatever cloud app you want to use. You can transform that data on the fly, do whatever you want. You can just have it immediately go to Azure, AWS, wherever you want to send it. There's other features in NodeHub that aren't as important today. Fleet management, there's over-the-air firmware updates you can apply to your devices, and NodeHub, again, is all about security. One interesting fact, too, is that the cellular note card, since it does not live on the public internet, it does utilize private VPN tunnels. Data can actually be encrypted, like data is literally sent off the internet, off the public internet. So to kind of help visualize where these things kind of fit in any given IoT solution at a very high level, you do bring your microcontroller, whatever it may be. It may be one of these that's running TinyCLR. It may be a more established one running Arduino or Python. You can use any sensors you want, any programming language you want, as long as it can read and write strings, basically. You compose what we call notes, which it's just JSON. It's just a JSON payload. Then you save those to the note card. There's about 2 megs of flash on the note card itself, so you can save this data. It's really meant for occasionally connected scenarios. You can imagine saving a set of data, and then at a cadence that you specify, that data gets sent to our cloud service NodeHub. Now, we don't want your data to live on NodeHub. Let me be very clear about that. We want you to optimize that data, to transform it, to route it out to your cloud. And again, that could be a big cloud. That could be an IoT optimized provider like a UbiDots or Losant or DataCake, if you've heard of any of those. You can also completely reverse this process from the cloud, and you can send these notes, these JSON packets, to a single device or a fleet of devices. You can imagine that might be useful for like a remote control scenario, for instance. So with that, let us see kind of a more real IoT project. And I want to show an end-to-end example of pulling sensor data onto a device, pulling data from a sensor, storing it on a device, creating a note, storing it on the note card, sending that over cellular to the cloud, and then to NodeHub, and then on to my cloud. And I'm going to show you all those 5 steps here in not too long. What I have in front of me here, I also put in a slide because it's a little easier to see. What you see in the middle of that green thing, that is the cellular note card. Again, it's really tiny, 30 by 35 millimeters. It slots into what we call note carriers. These are just development boards that make it really easy to interact with all the pins available on the note card. You see those red things are also antennas. So there's onboard antennas here. There's a whole row of headers there. This will work, yeah. This is where you can plug these jumper wires in to communicate with the note card / note carrier with your breadboard, which connects then to some pins on the microcontroller, and which I should probably plug in so we can see how this all works. And yeah, so this is where it gets power. So the red and the black is where it's going to get its power from the microcontroller, and the green and the orange pins let us communicate bidirectionally over this communication bus called I2C. And let's hope I don't screw this up. There we go. So let me. All right, I'm going to dare to run parallels again. And first thing I want to do is just show that I have NodeHub running here, and I'm not going to dive into NodeHub at all. Just know that this is like kind of the temporary store for my data. I have a project specific to this device called NDC, and you'll note that there is an identifier here. This is a globally unique identifier for this project, blues are Lauer :NDC. I'll come back to this in a second. Still, I'm not used to Windows 11. Oh, I have that open. Okay. So in this project, again, a pretty surprisingly simple project in many ways. Let's scroll through here quickly. I have a temperature class. This correlates to the card.temp API provided by the note card. That's because I'm cheating a little bit here. I don't have an external sensor. There is a temperature sensor on the note card itself, and I can get the value, which is the temperature in Celsius. There's also a calibration value, integer, that's set on the note card itself, so I can get both of those values out. And in my main method, what am I doing here? I am setting up the I2C bus for the feather to communicate with the note card itself. And then I'm going to go ahead and associate this note card with that NodeHub project that I created. Now, this is the first JSON request that I'm making, and this JSON request object here is unique to the note card, or sorry, the note card's SDK for TinyCLR. But all I'm doing is crafting a JSON object here, right? I'm creating a request called hub.set. I'm going to set this note card. I'm going to set the ID, the product ID of it, to blues are Lauer NDC, which you saw in NodeHub. And I'm going to set its mode to continuous, meaning maintain a continuous cellular connection. Not great for battery life, but much better for demos. And that ends up looking like this JSON object that you see there. Pretty simple, right? And if anybody has ever gotten into dealing with cellular in this arena before, you will appreciate how dead simple this really is. You're not writing these raw AT cellular commands these AT commands to interact with the cellular radio. It's just obfuscated away. I'm sending that request to the note card, and then we get into our infinite loop. And within that infinite loop, this is a very poorly named method called send data. We'll get into what that really means. And then I'm going to sleep for 20 seconds, and this is going to loop on forever. Skip that for a second. Here's my send data method. What am I doing here? Well, the first thing I'm going to do is going to get the temperature value from the note card. That's in this method. Again, nothing too complicated here. I'm simply sending this card.temp request, which is going to return a value that I'm going to deserialize into just this decimal value, or double, for the Celsius temperature. And then I'm finally going to get to creating my first note. And remember, a note is just a JSON payload of data. It's going to include a body parameter. That body parameter is just any arbitrary JSON that you want to send. It can be as simple as what I'm doing today, which is just that, you can see down here, that temperature, whatever the temperature value is. It can be incredibly complicated. It can be very long. You can send binary data, not through this way. You can send basically any type of data you need to send. The sync true parameter, just FYI, is telling the node card to immediately sync this. So it's going to save it briefly, but then immediately try and sync it with the cloud. That's all that the sync true means. And that's actually about it. So, and then send that request to the node card and do this every 20 seconds. So let's see if we can actually get this to work and deploy and get it at least to Node Hub. And build and deploy and hope for the best. So confused why HDMI is working, but I'm not, shouldn't even say anything. Yep, allow it again. Yeah, this is not surprising. So what I have to do to fix that is to literally do the same thing again. Or try unplugging it and plugging it back in. On a device, let's see. Yeah, I refuse to believe that this won't work. Oh. Here's what I'm gonna do. I'm actually gonna unplug HDMI because I ran into this the other day. If anybody was at our workshop, something about the power draw of HDMI on here it does not allow me to actually deploy something. So I'm gonna temporarily turn this off just so I can get the code deployed and running. Promise you. Nothing up my sleeves, right? I didn't know HDMI actually drew power from. All right, that's not working either. This is like the most classic demo fail that literally never failed before. I'm gonna restart Parallels. And tell my boss I need a real Windows machine. Holy smokes, there we go. And wish you could see my screen. It is freaking out about USB. All right, I'm taking you out. Pull everything out. That's not even plugged in. All right. That's not gonna work. This is gonna work. Okay. Now it's going. I don't want to plug this in quite yet. So it's building and deploying to the device. As soon as I get one success, I'm gonna hook up HDMI again. Stupid parallels. All right, I'm gonna show this in a different way then. I'm gonna disconnect you. No, it's not gonna work, is it? This is just borderline comical. All right, let's quit this again. I've got everything quit. Not even running anything anymore. Oh no. See, I knew it was going way too well for too long. All right, well. Nothing's plugged in. kill this adapter too. Okay, let's pretend we saw it working. What would happen? I'm literally just I'm gonna bring a browser up here and I'm gonna literally show you and hold this up. And maybe it'll come back on here in a second. Jack up the visibility here. So this again, which none of you can see, this is my note card for my my NoteHub project. I did have a device connection there. If you squint, you can see it actually connected. What's that one? Oh, different. Wow, that's crazy. All right, well, yeah, no, I mean, could be anything, as we all know. And I can navigate to some events here, and we can see, well, no events were found because I deleted them, of course, before I'm giving my demo. But what you would see here is that temperature data that was relayed from my note card to the cloud here. The next thing I was going to show you is how you can head to the routes section within NoteHub, and you can create a route. And I was going to route data live from here to webhook.site, which is a really cool place to kind of test and debug routing data. You just literally copy a URL, you paste it into your NoteHub route, and NoteHub will then immediately post data that comes in from your device to that endpoint. And so that was going to be the end of my demo. It's going to be really cool, and you're all going to be like rolling on the floor. Can't believe what's going on here. I do have a couple more slides to show, and I'm going to, where did my adapter go? Did I put it on the ground here? Let's just, as a Hail Mary attempt here, let's try and get this to work. If not, we can all go our separate ways and pretend this never happened. Oh yeah, that would be helpful too, wouldn't it? Nothing at all? Well, in that case, all right, well, nothing. All right, well, this is far and away the most anticlimactic end to any talk I've ever given in my life, but I thank you all for attending. Hey, for no reason, it comes and goes. Holy cow. Here, you want to see the slides? Let's see. Went through that. Yeah, again, oh wow, it's going to show, again, my point here, you do not want to store your data in NoteHub. You want to route that to your cloud. Maybe it's Azure. We have a bunch of resources on dev.blues.io if you want to learn more about those. Oh well. Yay. Well, hopefully you've kind of, you believe me and not the hardware that we can bring web developers and embedded developers together by using some of these tiny frameworks. And if you're curious to learn more, head to GHI Electronics or nanoframework.net to learn more about these two frameworks. And if you're even more curious about using our tools, head to bit.ly/blues NDC Copenhagen or scan that QR code for 20% off one of our starter kits. So with that, thank you all very much for attending and being very patient through our technical struggles, but yeah, thanks.